Welcome to research at TTIC. For those of you visiting for the day, this is you're sitting in on a weekly lecture series that we have with the different faculty speaking each week, presenting their research. And this week we're very happy to have Madhur Tulsiani present. So Madhur, professor here working, probably describe much better than me, like he's working on, but we're doing this complexity theory and coding theory. And we'll have, generally every week we have either different current faculty, such as Madhur presenting, or research faculty to really give a broad view of the activities. So Madhur promised an extra special talk today, and I'm looking forward to delivering that.
Right, everyone. First of all, say this is joint work with three excellent co-authors, Fernando, Tushant, and Shashank, who have are at various places, but a couple of years ago they were all students either at Chicago or TTIC. So, yeah, large wing for the visiting students. And I'll talk about some recent results in coding theory, and in particular, I'll explain the words in the title about expander graphs and sort of list-decodable codes and optimality, etc. But here's how I want you to think of the title, which is that we'll talk about how expander graphs, which also I define, lead to some very interesting and new kind of codes or sort of constructions for better communication. And I'll explain the technical words in this title as well, maybe not cool and awesome, but the rest. Okay. And this is the course for the TTIC students, or at least first year TTIC students. So you're also going to hear a little bit of history of coding theory. I apologize for the rest of you. And also just feel free to stop me at any point and ask questions. I mean, yeah. So error correcting codes. Basically, they are kind of method of communicating reliably. So in this talk, we are going to think of, we're trying to communicate, and there is some sort of adversary, maybe one that looks like that, and they might corrupt some part of what we send. And if we know, let's say they are going to corrupt one of the bits possibly, then how do we communicate reliably? Well, here's one way to do it. Let's just repeat everything 3 times, and if they corrupt one, I can just take majority of every position. Not that terribly, it's not kind of great. I have to sort of send 3 times as many things, and then at the end of the day, I just get to maybe handle one possible corruption. But I just want to point out that, okay, I mean, we'll talk about these sort of questions. What's the best way to do it, and what sort of a good trade-off between how much error we can correct, etc. But I should say that kind of codes are sort of something which are useful in lots of places, and we are using them all the time, even when we know it or not. And not just when we are kind of dealing with people who look like that, but all the time in real life. So actually, we are not talking in English right now. I'm just making some funny sounds, and you're mapping them to words or letters and so on. If Nati was to come up and say the same words, the sounds would be a bit different, but you would map them to the kind of same letters and words, and then we are not even going to talk about the concepts you derive from those words. Okay. So anything you have kind of ever said, heard, watched, your entire sensory system is actually an error correcting code, which is correcting the inputs you are getting and mapping them to somewhat robustly to signals. Same is true when we are kind of using any kind of digital information. Your hard drive kind of stores things in a code, and it's being transmitted over wireless, it's being encoded, etc. And then basically any setting where we want storage, which is just communication to our kind of future self, or just sort of actual communication right now between 2 people to be robust, somewhat secure, we use codes. And there are some kind of applications where these are crucial, for example, things like quantum computing, etc., where the noise is a big issue today. The difference between the very first bullet and the rest is that, well, the kind of code that we're talking about in terms of sounds to English is not something we designed, it just evolved. But the rest of them are codes that we get to design, we get to pick, and coding theory is about kind of how to design better code, so that's what we'll discuss in this. And for the purpose of this talk, we'll just kind of think of codes abstractly, just points in a space which are somewhat far from each other. And the idea is we'll think of an error as maybe corrupting one of these points to a somewhat nearby point, but if they're far from each other, we can still tell apart which point we were talking about. A little more formally, we'll think of code as just a string with, let's say, zeros and ones, or more generally, symbols which take value in a sort of set of size q, which we can think of as a finite field, which is kind of the numbers from 0 to q minus 1 with some modular arithmetic, but we don't need that for this talk. So you can just think of every symbol of some letter of size, in a space of size q. And so now think of q maybe larger than 2, but maybe 100. So nothing, and then we'll talk about q. And when I say these points are far apart, I'll talk in terms of Hamming distance. So the number of positions in which these strings are different from each other. Or in fact, I will actually not talk of the number of positions, but the fraction of positions. So I'll always divide by this capital N. So then the distances will be between 0 and 1. It's kind of, they differ in 50% of the positions or 70% of the. That's just how I'll think of a code. Any questions? So far, things are okay? And now, yeah, just to formalize what we were saying, that kind of far apart points help us fix errors. So let's say if any 2 points are at least delta far from each other. So delta is the minimum distance between 2 red points in this picture. And again, delta is a fraction between 0 and 1. And if anybody corrupts one of these red points in delta over 2 fraction of positions, then I can still uniquely tell you which is the point we were talking about, because these delta over 2 balls between 2 points cannot intersect because of triangulation. So I can always fix delta n over 2 errors, and this is kind of an if and only if. So distance is basically, if I want to fix arbitrary errors, it's the same as talking about distance of a group. Everybody okay so far? Or a point in space. Of course, just saying that I can do it in principle doesn't really solve the problem, and there is actually a very non-trivial algorithmic task, which is finding this kind of, if I give you something in a ball around one of these centers, finding that point is very non-trivial. And that is the problem of decoding. And there is a related task, which is, so you might have seen that here, if the distance is delta, we can uniquely fix about delta over 2 fraction of the errors, find the unique point. But there is this factor of 2. So you kind of, if you designed a good code, you can't really go all the way up to delta, or sort of can't really fix. So even if delta was really, really large, it's just a fraction between 0 and 1. If delta was even 1, you can't fix more than half the errors. You have to be correct at least in 51% of the positions to be able to do something. And there is a related task called list decoding, which we'll talk about much more through the talk, where the corruption is allowed to be a bit more, so maybe more than half the distance of the code. And we'll just call this parameter rho, which is the amount of corruption, which will possibly be more than half the distance. And now maybe we can't hope for finding a unique code word, finding the closest one, sort of the unique closest one. But maybe there are like 10 of them, so I can ask you, okay, give me all 10 of them and I'll figure it out. And that's what list decoding is. Maybe. And now there are 2 parts to this question. One, who is to tell me that there are only 10 of the code words? Maybe sort of once I kind of go beyond delta over 2, all hell breaks loose, and maybe the entire code is possible, and then so maybe there are just kind of so many points that I cannot even hope to write it down, sort of beyond the unique decoding threshold of delta over 2. And even if I was somehow magically to prove that, okay, there are only at most 10 of them within some slightly larger radius, how do you find them? And that's the algorithmic. Is it okay that these 2 questions are kind of both non-trivial at this point? There's something to be done here. We'll mostly just talk about the combinatorial question today, just sort of about saying, if I corrupt code word in a slightly larger number of positions, how do you show that there is only a small number of options? Okay. But first, I should say that, okay, I mean, one has to be a bit careful in asking this question, and this kind of delta over 2 threshold is not really the right number to compare yourself to, because I can just lie to you. So I might have a code which has a great distance, distance between any 2 points. Any 2 points in the code differ in 90% of their position. So the actual distance is 0.9. I'll just tell you that the distance is 40% or 0.4. And sure enough, then I can claim, okay, I can actually list decode it even with 45% of error, even though the distance is 40%. Because I know the distance is 90%, so this is doable, but I just didn't tell you. And I can even say that, okay, the combinatorial problem is solved perfectly. The list is always of size 1, even when I corrupt in 45%, even though the distance is 40%. I'm just lying. And at that point, Nati will be justifiably suspicious of anything I ever say out loud, which maybe he already is, but
nothing personal.
Sorry?
Nothing personal.
I know, you're suspicious of everybody, but that's fine. So, okay. And I mean, I might not have to lie, right? In some sense, the distance is a worst case quantity. It's really saying what is, like, the entire code of all the possible kind of red dots in this picture, what is the sort of worst possible distance between 2 closest dots? And I can just add 1 bad point to the code, which will kind of reduce the distance. Everything else will stay the same. And so the distance can actually be 0.4, or at least I can kind of even delude myself into believing that it's a code with distance 0.4, but it's really a code with distance 0.9. I just added 1 bad point or a few bad points, and maybe once in my life I'll have to give you a list of size 2, but every time else this is just good. So it's not the right kind of way to ask this question. And I have to somehow tell you that, okay, I'm giving you a distance which is kind of as large as possible. And maybe even if I can remove a few spurious bad points, at least then I'm giving you, so for a code which is as large as possible, I'm giving you the right kind of distance. You look suspicious. Okay.
So okay, I'm a bit suspicious because
sure.
In some sense, maybe the right, I mean, why are you doing this in the first place? And presumably you want to show me, the question I should have asked you is, why are you doing list decoding in the first place?
Yeah.
I mean, what I want you to convince me is by returning to me multiple answers, you can do better than, I don't know, Shriyan that insists always returning me one answer.
Yes. So we will get to that in a minute. But let me just formalize this question a little differently. So I'll kind of talk about distant in terms of how large the code is or how big this collection of red dots is. And that's measured by something called the rate of the code, which is basically the amount of redundancy in the code. So it's just the log of the number of red points divided by log of the size of the whole space. So if I wanted to communicate to you an arbitrary point in this whole space, I will need the log of q to the n bits to sort of tell you the sort of name for that point. And if I wanted to communicate to you one of the code words, without any redundancy, it will take me log of c bits. And so roughly, what is the kind of fraction by which, or 1 over the fraction by which I'm overpaying here. So this is just a measure of the redundancy in the code. And there is kind of a nice bound called the singleton bound, which doesn't come from a singleton set, but a person called singleton. It says that the distance is always, again, these are both fractions, delta and r, and distance is always at most 1 minus r. So in some sense, if I give you a code with distance actually equal to 1 minus r and rate r, then I can't really lie to you about a distance. I can't have the distance is 1 minus r, so it's kind of as large as it possibly can be. And the rate you can just check, you can just count the code words. So you don't need to believe me. And so one way we can ask this question is, okay, I'll give you, and then first the proof of this singleton bound, again, coding theory class, but nothing that mysterious. If you just kind of take any 2 code words, fix or partition them into 2 parts, just the last delta n minus 1 positions and the rest, then any 2 code words differ in delta n positions. That's just our assumption in terms of distance. That's what distance means. Any 2 code words differ in that many positions. So because the last half doesn't have enough space, they must differ in at least 1 position in the first part of the picture. So the number of code words is at most the number of different ways of filling the first part of this picture, which is just q to whatever is the number of positions, and you take log, you get singleton. So that's just a proof of singleton. I mean, don't worry too much about it, but this delta less than 1 minus r is somehow a way of saying I'm giving you, or like if I promise this, then this is the best code I could have given you. It doesn't have any of these bad points occurring here and there, destroying my distance. And now, let's think of the distance as really 1 minus r. Now let's think of r as 0.1, for example. So the distance is 0.9. And if I could kind of list decode up to, let's say, even this 1 minus r, 0.9, what does it really mean? Unique decoding means that I have to give you something which is corrupted in at most 45% of the positions. So 55% is correct. Corrupted in 0.9 positions means that I'm only giving you something which is correct in 0.1 fraction or 10% of the positions. You don't even know which one they are. But you can still narrow it down to 10 things out of this whole space, which is exponential size, right? Because if the rate is constant, this size of the code also has to be something like q to some constant times n, q to the rn. Right? So list decoding kind of, in that sense, is almost unbelievable that I'm giving you a code which is corrupted almost everywhere. Okay? Maybe just 10% of things are correct. I'm not telling you where the correct things are. And you can still narrow it down from this exponentially many possibilities to just a small number, so 10 or 20. And that by itself is kind of almost a miraculous operation. It also has lots of applications in kind of complexity theory or communication when we want to be able to handle more than 50% of the corruption or be able to robust to much more noise. And yeah,
just about what applies to what order of first. When you say that you always get a constant size list as long as delta is less than 1 over squared bar. Is this for any code?
Yeah, I haven't gotten to that part. I'll explain.
Like the existing code?
Sorry, this is true for any code, but I'll get
any code. Yeah. So for any code with rate r, no matter
not any rate r, the distance kind of 1 minus r, or sort of in general for any code with distance 1 minus eta. And q which is large enough, so think of q as like, if you want to be epsilon close to this, then think of q as larger than 1 over epsilon. So I'm hiding about something about q. Otherwise the bound is slightly more complicated. Up to this distance, you can always get a list of size at most some 1 over epsilon square or some sort of constant in terms of epsilon. So for absolutely any code, if I tell you that the distance is close to 1, then you can actually list decode it close to 1, at least combinatorially. The list is bounded. This is something called the Johnson bound, which I'll not discuss too much today, but yeah, I mean, it's sort of it's something we talked about maybe, I mentioned in my talk 2 years ago when I was giving the same talk, I was talking about Johnson bound. I should say, even kind of, but even before we got to the Johnson bound, sort of, I just want to fix a setting where we are thinking of codes with distance which is as large as possible. And now we are going to ask the list decoding question. So your distance is 1 minus r. Now what can you do? And even if this sort of list is always bounded, the combinatorial question is solved for all codes, at least up to root r. The algorithmic task is highly non-trivial. In fact, one of the most celebrated list decoding algorithms, the first one, was by Madhur Tulsiani for a set of codes called Reed-Solomon codes, which I'll get to in 97. And then sort of this had an extra factor of 2, so it was sort of 1 minus square root 2r, and then improved by Guruswamy and Sudan, which are all kind of some of the more foundational results in this area. So even algorithms for a very specific code have been very non-trivial. But today, we're not focusing on algorithms, we're just asking about the combinatorial question. So that one is kind of solved up to 1 minus root r. So then we will kind of ask, okay, now if we are looking at distance which is 1 minus r, then the right way to ask the list decoding question is, can you do better than 1 minus root r? Can you do beyond sort of the bound where the combinatorial question is kind of just trivially solved? Any questions? And beyond this, sort of much less is known. And in fact, it took quite a few years to even show that there exist codes. Well, okay, there exist as a sort of qualifier. You can always take random codes and they do very well. So you can show list sizes are bounded beyond. In fact, you can go all the way up to distance 1 minus r, but there's no hope of an algorithm for working with random codes. And also, not always even clear to possibly to verify if I give you a random code, how do you actually check that it has these good properties? So it's okay if we don't want to talk a few times, but if you want to kind of use that code, ship it in some software in an airplane, maybe you want to verify it more carefully. So even to kind of show that there are codes where you can go beyond this, took some fairly ingenious ingenious constructions, and Parvarish Wadi were the first ones to give kind of an analog of these Reed-Solomon codes, which which are basically defined using polynomials, and I'll not get into them too much, but they use some sort of algebraic techniques to sort of talk about list sizes and so on. The problem with Reed-Solomon codes is, the way they are defined is you just kind of take a polynomial and evaluate it in a bunch of points and just write down those symbols. But you need even enough points to evaluate it on, and so if you want to write down n symbols, you need n evaluation points, and so the space in which you are doing the evaluations, which is the underlying field, has to be of size n. So Q is really, really large for this. And just to think about what does it mean to have a large Q. You're not going to magically build some machine which kind of sends big symbols in one shot. What you are going to do is maybe send it through bits and maybe communicate to me sort of log n bits to send me a symbol of size n. And when we are saying Q is large and kind of 90% of the things are corrupted, 10% got through uncorrupted, it means that 10% of these blocks, contiguous blocks, didn't get corrupted. So at least it happened 10% of the time that a block of size log n did not get corrupted at all. And so it's a stronger assumption. Like every time you send me a big block, it kind of takes a lot to say, okay, this block did not get corrupted. And sort of, at least even saying that for 10% of the blocks is kind of hard. But building on these, you can get codes where you can do excellent kind of list decoding. You can get all the way up to 1 minus r if the rate of the code is r, which is, again, a variant of the singleton bound can show that this is basically the best possible. So this is the distance up to which you can even hope to do any kind of list decoding. And you can do that for these codes. And the sort of slightly more sophisticated variants called folded Reed-Solomon codes, which achieve this, and then there's some other things which use kind of algebraic geometry or some other properties. That's sort of the picture in terms of how well we can do list decoding. And then there is actually kind of a slew of bounds which are trying to say, okay, well, you can correct errors up to this many corruptions. What is the number of things you output? What is the size of your list? You want it to be small, we said 10, right? But at least the first bounds did not look like 10. So if you are epsilon close to the maximal possible number of errors, then the initial bounds were of the form exponential kind of n to the 1 over epsilon. And then kind of a lot of interesting ideas went into improving this to maybe some constant, but depending on epsilon. And then last year, which was kind of appeared this year, a paper by Shashank from TTIC, which was the best paper at SODA this year, which actually showed that you can get 1 over epsilon square, even at 1 minus r minus epsilon. So for folded Reed-Solomon code. So this is still for all this very specific algebraic construction. And then a kind of work of Chen and Zhang, which was independent of Shashank but appeared later, was it showed 1 over epsilon. So there, at least now we can say you can correct as many errors as theoretically possible. You can do it with a list which is not too large. And again, we can show that 1 over epsilon is optimal. So this list size is basically the right one up to the constant. So that is the sort of state of affairs in terms of list decoding. And this is just a bit of history, but any questions before we proceed? Okay, so seems like we're done. Right? We can kind of actually go all the way up to the maximum number of errors. We can correct them. We have codes which do that, and they can actually come with algorithms, or at least some of them do. But there are a few issues. One, as I said, all of this is based on some kind of non-trivial algebra, which I don't know. So, first thing is, well, to understand these things, you need to maybe understand some, at least non-trivial kind of algebraic facts. The second, which is actually a practical issue, is that we said the alphabet size for this code, which is just the assumption on what block sizes go through uncorrupted in one shot, is pretty large. And in fact, already for Reed-Solomon, this was, if you are giving n symbols, then each symbol needed to be in a space of size n. And for these folded Reed-Solomon codes, it's even worse. It's kind of some large exponent of it. And then there are other problems, like these polynomial-based constructions are a bit rigid. So sometimes we need additional properties of the code, like maybe you can spot check a code. You can kind of say that you can test if something is a valid code word or not, but just by sort of doing some sort of a large number of but local checks. And this is needed, for example, when you're designing codes for quantum computing and so on, where you want to just kind of look at every qubit which just wants to look at its neighbors, and as long as everybody is happy with their neighbors, the whole thing is uncorrupted. So these sort of spot checks, which are called LDPC property, low density parity check property, you don't get it from these polynomial constructions, and we would like this, particularly if you are designing kind of good codes. And for me personally, a bit more of a philosophical question that, okay, I mean, we saw that 1 minus root r is always doable for any code. And it seems like anytime we want to go beyond that, we have to use this kind of algebraic machine. So is it really the case that kind of list decoding is something of an algebraic phenomenon, or is there something more general going on which one can kind of do without some of these specific algebraic arguments? So this is a question I want to talk about. Any questions? Right. So actually, the result I'll mention is basically a very elementary construction of codes, which does all of this. So you can correct, again, the best possible number of errors. You get the best possible size of the list. The alphabet size, or the size of every symbol, is actually a constant. It doesn't grow with n at all. And you can get a lot of other properties. So in particular, you can get these spot checking properties, etc. And in fact, it does even something even stronger than list decoding. It achieves something, or it gets arbitrarily close to something called the generalized singleton bound. I'll mention that in a minute. But so this maybe, as far as I know, the first construction of codes with constant size symbols, which can do this kind of list decoding, and then it has the additional benefit of being sort of a fairly elementary one. Any questions about the result? I'll describe the last one. Okay, so what do I mean by this generalized singleton bound or whatnot? So we said any code has distance at most 1 minus r. Another way of saying this is that if you want to decode with a list of size 1, which means if you want to unique decode, you cannot handle more than 1 minus r divided by 2 number of corruptions, right? Half the distance. So half the distance, which is the radius within which your sort of list is of size 1, is at most 1 minus r over 2. And the generalized singleton bound, which was defined recently, says that if you are shooting for a list of size 3, then you cannot do better than a list of size 2, so strictly less than 3, then you cannot do better than 2/3 of 1 minus r. Or if you are shooting for a list of size at most 3, then you cannot do better than 3/4 of 1 minus r. So in general, if you want, so the contrapositive, if you want to get arbitrarily close to 1 minus r minus epsilon, you have to think of this k as 1 over epsilon, because the gap from the optimal is about 1 over k. So if you want to get arbitrarily close, then you need a list of size 1 over epsilon. And what we can show is actually something which kind of achieves that kind of a bound, or is close to that bound for every k. Not just sort of k equals 1 over epsilon, which would be sort of 1 minus r minus epsilon, but for every k. And formally, what we show is that even a stronger version of that, which is pick any corrupted word around which you are going to try and do list decoding. So this is going to be the center, and then we are going to find code words around it. And take any k code words, and now measure the average distance of these code words from the center. this is going to be large. It's going to be something like k minus 1 over k times 1 minus 1. What that means is that if you have k code words, they cannot all be close to this center, not closer than whatever is on the right hand side. Right? So you cannot have k things all whose distances are less than this, because the average distance is greater than this. So if you around any center, if you draw a ball of this size or this radius, then the number of things which are inside that ball is at most k minus 1, strictly less than, because the average distance of k things is too large. Yeah.
So if list size is k is 2, so list size is smaller than 2, then you get the row is smaller than half of 4 minus r.
Yeah, so strictly smaller than 2 is 1. That's the unique decoding radius.
Yeah. But
that's the singleton bound already, right? So if you want lists of size 1, which means if you want unique decoding, then you cannot do better than half of 1 minus r. So the distance is 1 minus r, so the unique decoding radius is half of 1. So that is the classical singleton bound. And this generalization is, if you want list of size strictly less than 3 or at most 2, then you cannot do better than 2/3 of 1 minus r. List of size 3, then you cannot do better than 3/4, and so on. So if you want to get close to 1 minus r, you better be willing to handle lists of size 1 over epsilon, and we can get them. But even this is a stronger conclusion for every case. Any questions about the statement? By the way, yeah, this Chen and Zhang paper from 25, as I mentioned, also shows this for folded Reed-Solomon code. But again, the problem there is you need these really large symbols of size n to the 1 over epsilon square for every symbol. And then this one doesn't need it. Yeah.
Do you have any codes that achieve this bound?
I'm sorry?
Do you have any codes that achieve this?
Yeah, our construction actually achieves this. So achieve as in with epsilon equals 0? Or just for every positive epsilon?
That is optimal in some way.
I'm sorry?
That is optimal in some way. You just.
So yeah, for every positive epsilon, we can give codes which achieves this bound. If you need epsilon equal to 0 here, then it's actually known that you need alphabet size which is actually exponential in n, not just constant. So you cannot have codes with constant alphabet which achieve it with epsilon equals 0. But any positive epsilon, yes, I'm going to give you codes which do this. So yeah, take epsilon to be as small a constant as you want, and we can do this.
Wait, but you're saying that even 0 is principal?
Sorry?
So even the 0 is achievable?
So there is a construction, I think, for k equals 3 or something, but it requires a kind of alphabet which is exponential in n, and necessarily so.
But specifically for k equals 2. Okay, sorry.
No, I think, no, sorry. There are these things called higher order MDS codes which are known for every positive k, but the alphabet size is exponential in n. And it's known that even for 3 you need exponential in n, so sort of goes. And yeah, also folded Reed-Solomon codes which I mentioned also achieve this model. Again, with this sort of epsilon slack, because the alphabet size is n to some large power, so it's polynomial in n, not exponential. So they also need a slack. We can do this with constant, but yeah, these are the two things I know which achieve this. And random codes achieve this bound. So if you just were to pick a code at random or a random linear code, which is just pick a random matrix and look at its image as a generator matrix, they will also again get arbitrarily close to this bound for every epsilon. But random codes don't come with algorithms. Does that answer? Other questions? Okay, so I promised something about expander graphs. Let me just tell you a little bit about expander graphs and maybe show you what the construction of the code is. And we don't really the proof is very, very simple, but we'll see. I don't know if we'll have that. But if you've not seen expander graphs, they're really cool objects to know. For this talk, I'll think of bipartite graphs. So let's think of n vertices on each side, and then kind of have a graph where every vertex has degree d, so it has d neighbors. So on both sides, it's kind of regular on both sides. And we'll give a spectral definition, or sort of in terms of eigenvalues or singular values, to say what it means to be an expander. So you can just think of this graph as a matrix. Rows correspond to the left side, columns correspond to the right side, and you have a 1 if there is an edge between kind of a vertex L and vertex R, and 0 otherwise. And this is not necessarily a symmetric matrix, but we can think of its singular values. And just the way I said it, every row has sort of exactly d ones, and the rest of them are 0. So the maximum singular value is at most d. If I divide by d or kind of write this 1 over d in front, then the maximum singular value is at most 1. And so the singular values are between 0 and 1 for this matrix once I sort of normalize. And we'll just say it's an expander if the second singular value is smaller than lambda. And think of lambda as 0.01, so something much smaller than 1. The largest one you can show there is going to be 1. So you can only talk of the second one. That's just the definition of an expander. Are you okay with singular values or some of the spectral definition? I mean, okay, I'm not going to use much about it. The only fact I need about expanders, which is an exercise in a class where you can teach singular values, is just saying that if you want to count the number of edges between any set S on the left and T on the right, and if I just threw in edges randomly, so if every edge appeared with probability d over n, then the number of possible edges I could have had is kind of number of vertices in S times the number of vertices in T. And so this is the expected number of edges when I'm just throwing them in at random. And an expander kind of gets pretty close to it for every S and T. So for every set S and T, the number of edges is the same as a random graph up to a small error, at least a small error when lambda is small. In fact, this is a weakening of the bound. I mean, the n can be replaced by some sort of standard deviation kind of term. Again, it's an exercise once you know singular values. Everyone okay with this particular property? Number of edges look like those in a random graph. And there is something called the expander mixing graph. It's very simplistic. And actually, the construction we sort of give for codes is basically a new analysis of an existing construction from 30 years ago by Allen, Edmonds, and Luby, which was originally designed for kind of giving codes with kind of good distance and rate properties. And we can show that it also gets these optimal list decoding kind of properties. And the construction is very simple. You take, let's say, an expander graph, n vertices on both sides, everybody has degree d, so everybody has d neighbors. And then you start with n symbols, which each of them will be sitting sort of on one vertex on the left. These n symbols are thought to come from some sort of starting base code, which we'll call C0. We don't need too much about it, so for now, don't worry about it. The only thing I'll say is that think of each of these symbols as small bit strings, so of size k, where k is some small constant. So everybody has k bits, every vertex. Then we kind of encode what every vertex sees using some small code which maps k bits to d bits. So I'm thinking of k and d both as constants. So k is 7, d is 10. So I'm just kind of mapping 7 bits to 10 bits using some kind of small code that is present at every vertex. So now everybody had 7 bits. I encoded them. Now everybody has 10 bits. And d is also the number of edges. So I have 10 bits. I have 10 edges sort of across, sort of adjacent to me, or 10 neighbors. And I just kind of write one bit on each of my sort of edges and just send it to my neighbors. And the neighbors collect the things they get, and sort of they have d neighbors also, so they get d bits. They just package them together and write down d bits that they see. The whole thing is just kind of a repackaging operation, except for this small bit of encoding here. But this is a constant size object. It's just mapping 7 bits to 10 bits. And now everybody has 10 bits on the right, which they kind of got by repackaging the bits they got from their neighbors. That's the entire construction. That's the code. And then we can parameterize it by what we started with and more importantly, what this 7-bit to 10-bit code is. That's the only thing that actually matters a lot. It's just described in terms of this very small constant size object. The new alphabet I'll think of as 2 to the d. So everybody has d bits, which they collected from their neighbors. So I'll think of d is a constant, d is 10. So I'm thinking of the alphabet as 2 to the 10, not going with n anymore. And I'm going to say two symbols are different in this space of size 2 to the d if they differ in any of the d positions. So if I had two symbols which correspond to what I see on the edges, if any one of the edges is giving me different information, these d-bit strings are differing in one of their positions, and I call them different. Is everyone okay with what the code is? It's kind of sent one way, repackaged the other way, that's it. And what they can show this was the Allen Edmonds and Luby table, that these codes have an amazing kind of local to global property. If this small code, this thing that maps 7 bits to 10 bits that we chose, has good distance and rate properties. So if it kind of had the singleton bound-like behavior, that the distance was equal to 1 minus the rate. For this small constant size code, then you get it for the whole code. Then you get it for this global. So if you found a good code on 10 bits, you can find a good code on n bits for any growing thing. And for 10 bits, you can just do brute force search, and there's nothing that sort of mysterious about it. You need some things, you need the starting base code to have high rate, but you don't really care too much about its distance, so you can take any existing code constructions and modify them to get this. This is fairly elementary. And you need this spectral gap or lambda, which is kind of quantifying the expansion to be very strong. But again, we know lots of constructions of expander graphs, so this is just kind of easy to arrange. But once you have this, it all boils down to just picking this small object. And once you get a good small object, it gives you good distance. This is for distance, so constructing codes which have distance 1 minus the rate of the code and kind of arbitrarily close to it. Is the claim okay? I'm not proving it. I'm just sort of seeing if people understand what the statement means. It gives me a way of taking a good code on 10 bits and sort of mapping and creating a good code on any number of bits I want, as large as I want. And as long as this small code had good properties, we can prove that this whole code has good properties. And we can actually do the same for list decoding. So what we can show is, if this small code, if this code has this kind of average distance inequality, that if I kind of take k things, take their average distance from a center or the sum of their distances from a center, and if this is large, then this big code also has the same property, that sum of distances from a center is large. So you get this local to global. Again, all you need to do is find this kind of small 10-bit code. 10 is an arbitrary positive number, but yeah, some small code. And again, we can find this just by enumerating, so there's not much. And once you find this, it's just this repackaging operation that you need to do. That's your code. Nothing else. Any questions? Okay. Let's see. Maybe I'll just do one small slide about the proof, just to see where this kind of local to global kind of comes from. In the original proof in Allen Edmonds and Luby, I'll not tell you really all the details in this proof. But we want to show that this code, these global code words, have some good properties, like any two code words are far from each other. So if I write down some global code word X and Y, they are far from each other. How are these obtained? Well, they are obtained by kind of these bundling, these things that I saw on the edges. So for every global code word, I can also think of it as packaging of something written on the edges. Let's send them back. So let's look at things on the edges. And now locally, every left vertex kind of sees these little code words with 10 bits, which is just whatever its neighbor sent it back. Just repackaging in the reverse direction. So you get these local, what I call local projections for these global code words. And I claim that these local projections have good distance, then these global things have good distance. That's what we wanted anyway. And that's just what it's just an expander mixing lemma from what we saw. Let's just look at the set of left things where the local projections have large distance, where the local things are far apart. And let's sort of mark the edges on which the local things are different as red edges. So everybody in S has a lot of red edges. That's what it means to be in S. Locally things look different. So on every edge on which they look different, I just color it red. And then let's just look at all the right endpoints of these edges. Let's call that T. And now I'm just going to count edges. I have one way to count edges, which is the number of edges between S and T by expanded mixing lemma is something dependent on the size of S, size of T, whatever. And I also know that everybody in S is sending out a lot of red edges. So that the difference they see locally is theta, so it's sending out theta times D red edges. Rearrange things a little bit, and you get that theta is at most and every endpoint in T receives a red edge. It gets a red edge means that there is at least one neighbor on which X and Y are different. So X and Y are different from this sort of vertex counts them as different. So the size of T is basically a lower bound on the distance of X and Y, because on every vertex of T, X and Y are different. Because it has one witness. One neighbor is telling it that they are different. And then what this means is that, again, you can choose parameters right. Then you can say that even if an epsilon fraction of left vertices think that locally the distances are large, then globally that they have to be large. By contrapositive, sort of the number of people on the left that are hallucinating, that are kind of thinking that the distances are large but they are not large globally, has to be smaller than epsilon. So even if an epsilon fraction of them did think the distances were large, it would actually become large. It becomes reality. So almost everybody on the left is kind of not hallucinating. They are thinking that the distances are actually smaller than them. And that just tells me that on average, if things are far apart on the left, then they are far apart on the right. But on the left, being far apart just means being far apart in this kind of 10-dimensional space. And we chose a good code there that happens all the time. So it kind of basically happens on the right. I'll not go through the proof for our case. It just instead of saying that two things are far apart, now I need to kind of draw a ball and say that the average distance of three things from the center of this ball is large. Which again is kind of, I can just transfer it pair by pair. But yeah, some things which I need to be careful. Okay. That's basically all I'll say. But I wanted to point out that, okay, there is some sort of very simple code constructions. We can actually do list decoding as well as the best known constructions, can get better bounds in terms of alphabets, etc. There's also an algorithmic analog of everything I said. So these things can be done by polynomial time algorithms. Although the polynomial time algorithms right now use some semi-definite programs and they're not the most efficient ones. And so that's one of the questions. And this kind of gives us actually a paradigm for sort of taking these code properties in some constant size objects and then just extending them to very arbitrarily large code families. And yeah, one thing to think about is maybe, so is this doable for other kinds of code properties? It actually gives a scheme for construction, not just
questions? Okay, I have a question and an answer, and a question about whether my answer is a good answer.
Okay.
So, I'm curious, how do you use list decoding? Because at the end of the day, I need the decoding.
Right.
And maybe a possible answer. I don't know. I'm curious if you can see relationships here to AI or machine learning systems which can't maybe find the right answer, but have explore a small set of answers.
Right. So to answer about list decoding, so I'll give maybe two answers. One, I can have some side information which is not captured in a code, which is a way of verifying correct answers. So sure, so the code is just, I've kind of abstracted out these things, just point look that far from each other. But maybe I need some sort of additional answers like, okay, maybe you can map my sort of sounds to words and kind of think of a code at the level of a word. But then words have to form sentences and there are sort of consistency relations, and if sort of you get two sentences but in one of them kind of words are in some random garbage order, you can probably reject that sentence. So maybe if I'm doing this decoding multiple times and if I have extra correction, sort of extra consistency checks, I can live with list decoding by just sort of patching them together.
So why wouldn't I incorporate that into the code itself?
I'm sorry?
Why wouldn't I incorporate that into the code itself?
It depends on the model, right? So I mean, somehow, maybe I don't want to think of a code with, I want to think of a fixed code, which is at like a fixed word or n-gram level rather than kind of arbitrarily long paragraph levels. So maybe I don't want to think of arbitrarily large codes. I mean, I want to think of arbitrarily large codes, but at some point I want to fix an n and then work with it. And then maybe the consistency is whatever n I fixed, sort of at 10n or some larger fraction of that check consistencies. Okay, that's one answer. The other can be, it's not always true that all you need is decoding, because sometimes, and which is maybe related to the first answer, that we can try to kind of boost this. So sometimes I want to just be able to answer correctly with probability epsilon. And then I have an algorithm which can maybe boost it, and then if I have just something which can correct probability epsilon, then I can get sort of larger and larger values. And if I get a list of size 10, if I pick one of them at random, I will give you a correct answer with probability 1/10. And then, yeah, I mean, consistency is kind of maybe something with boosting it with probability 1, but maybe I can have some weaker kind of boosting. So, and then that, for example, in things like average case complexity, in things like PCP, in the theoretical applications, this is the way you actually use list decoding. You sort of think of being able to just answer with some small probability, and then you have a separate piece which can actually boost it. So those are a couple of answers in terms of this decoding. Can you repeat your question about machine learning systems one more time?
So you can think of situations where it's, I'm just trying to understand if we can take from this the systems where you frequently maybe can get a list of possible answers. Like you can think of it even, even very specifically to think of it using GPT or something like that, some language model, and you ask a question and you can get a bunch of different possible answers, or really it is a decoding there, because you get a distribution of it in the most likely ones. I'm trying to understand if we can borrow ideas from this decoding there, if we can map results.
I don't know sort of formally what to say about how list, but I mean, it does give list decoding, right? I mean, so sort of when I was preparing this talk, kind of asked ChatGPT, okay, I mean, sort of maybe what are some applications of coding theory, right? And then it sort of gave me a list which included things like QR codes, it included some other things, some of which I threw away, some of which I modified, and some of which I kind of included as such. So it actually, because a lot of the time my question is not well phrased, and so the only sensible answer is a list. I don't know how to think of kind of a not well phrased question as a highly noisy code. So that maybe is how I would, at least in one application, that's how I would like to think of it. It's, that it can be, so somehow this can be possibly completed to many messages. Like it can be, this question can be completed to many questions, and then each of those questions might have a unique answer. But somehow I want to think of this question as a distribution over questions as a noisy message. Okay, but yeah, we can talk about it.
Other questions?
Yeah, on the phone, not this question. So I think at the beginning of the talk, you have like adversary, like kind of like whenever it's a code communication process. But is this the coding still useful if we don't have that adversary? Say like when you chat with ChatGPT, like there's no such adversary, everything is maybe the correct way. Is it still useful? Like when we don't have this?
Yeah, so I mean, first of all, adversary is not really kind of adversarial or malicious or nefarious, irrespective of the picture I showed. It's just a proxy for an error process which we don't understand. Sort of, we want to say that, okay, I mean, if I really knew that every bit was getting corrupted with probability 1/10 or something, then there is a very clear understanding of that process. If I don't understand it, I kind of just try to design codes which can handle any kind of arbitrary error process, and that I call an adversary. And I think it's still fair to say that, at least in machine learning systems, if I think of some underlying error process, at least I don't understand it, and I don't know what the state of the art or what you might say about it. But when I don't want to make very strong assumptions about the error process, I think adversarial codes are still relevant.
What is 5G?
I'm sorry?
What is 5G?
I don't know. So, you mean the 5G communication standard? It's no, I don't know.
I mean, presumably, high bandwidth telephony, cell phone,
Right.
is relying heavily on coding.
It does, yeah. But I don't know the kind of the engineering details of it. Yeah. there's this Dilbert cartoon where like for our next communication scheme, we are going to call it 8G. And the engineer is, you just can't call things. There are specifications. And then there's a meeting in the marketing department. Guess what doesn't mean goodness? It's,
So maybe a different question is, I know like 25 years ago, people were studying graphical models,
Yes.
and LDPC emerged with message passing algorithms.
Right.
Do you know if that's still sort of the standard in practice? I mean,
Yes. So LDPC codes, again, I'm not kind of an engineering person, but from what I understand, they're still used quite heavily in practical applications. And so one of the motivations for us not coming from practical applications, but was to design LDPC codes with list decoding. And before this, we didn't really know of examples where you could do this, at least not with very good list decoding. That A is used in kind of telecommunications, and B, from what I understand, it's also quite relevant for these quantum applications, again, because you want to be able to verify corruptions by local checks in a quantum system. Their local actually also needs to mean spatially local, which is not captured just by the definition of LDPC. But, these things can also hopefully, at least, I think they can give quantum codes, which also have this kind of larger noise tolerance.
Okay, any final questions? Okay, excellent. So let's thank Madhur again. And